So, hello. We are one of the Spider Sense teams. Our project is called Ninja Vision, and it's me, Victor, Brad, and Brian. A small introduction. Let's look initially at the definition of what is a sense. According to Wikipedia, senses are physiological capacities of organisms that provide data for perception. As we know, human beings have 5 senses, but in the comic books, we can see that some heroes have additional senses or superpowers. So, for example, Spider-Man has what we call the spider sense, where when somebody from his family or close environment is in danger, he feels like a tickle behind his neck. Then we have the Green Lantern, where when he wears the ring, he can kind of feel the environment in a different way. Of course, he has superpowers, so he can travel in time and do a lot of nice things, but at the same time, he can kind of get a feeling of what's going on. And finally, I mean, there are a lot of other examples, but we just selected 3. Finally, there is Luke Skywalker and the Force, where, he kind of using the Force when there is great danger, or like when that planet disappears, he can kind of feel that. So the questions here are, can we enhance our powers? What happens if we add an additional sense? And how can we do that? And based on the definition, can we add one more physiological capacity, one or more, to provide an input channel for perception? So what we're going to, our project, it's kind of the same like Daredevil, where Daredevil is blind, he cannot see, but he kind of feels the environment. So Ninja Vision, the concept is the same. Ninja Vision allows you to feel the environment, feel the room, and you don't need vision anymore. Our goals here are, 1, aid visually impaired people to walk and navigate rooms. B, people who already have perfect vision, it will allow them to see in the dark, have eyes in the back, and maybe offload the information from your eyes to your body and see what's going to happen if they do that. So this is not a new idea. People have already thought about that, and already from the 1970s, they have looked into wearable tactile devices that convey messages to the body. So for example, in this picture, you can see a subject that has lost touch, so he cannot feel anything. So he has pressure sensors on his fingers, and he wears a headband with tactors. So every time he touches something, he can feel the pressure on his head. As we continue and we go in 2001, in the proceedings of the wearable computers, Gemperle discusses the design of a tactile display, issues and opportunities, and also gives a nice definition about what a tactile display is. So a tactile display is a display which presents information to the wearer by stimulating the perceptual nerves of the skin. So what that means is, it's a device that you wear and it has a resolution, and you can feel on your skin information using usually it's vibration motors, which are called tactors. In 2003, Jean Van Herp designed a vest for astronauts, so they can get the feeling. So this vest stimulates the whole body. It has a lot of vibration motors, as you can see, and objective of the vest is to have a localization of other astronauts and objects. So for example, you feel on your body where the space station is, so you don't get lost, or you feel on your body where other astronauts or Mother Earth is. 2004, Tsukada, in the proceedings of ubiquitous computing, he designed a belt that can navigate users to target directions using vibration. So you have your phone, you select where you want to go, and it has a GPS sensors, and you kind of feel which way you have to go. It doesn't take into account buildings, roads, nothing. It's like a compass. It tells to you, you have to go that way. And in the user study, people actually found that useful, and they were able to navigate at the target direction. But one other thing they were doing, the scientists here, is they were indicating distance in pulse intervals, and the subject said that it was very difficult to recognize and decode the pulse interval so that they can know how much distance is left. 2004, Jones, he wanted to evaluate vibration motors and kind of see if people are able to identify patterns on their back. So he put 9 vibration motors, and then he started playing back patterns, up, left, right. And it's very interesting that 85% of the subjects recognized the pattern. The one that was the most difficult to recognize was the diagonal one.
That's truly immersive.
And also, he's the first one that uses an actuator. He did a preliminary study on actuators, and the users perceived that as a firm pressure, as the skin was being prodded by a finger. What an actuator is, it's a device that goes like this. So you kind of, it's not a vibration motor that has 2 states. You kind of feel a lot of pressure or less pressure. 2005, Cardin developed a vest again, 2 ultrasound sensors that give you depth information and 2 vibration motors, and people were able to navigate in the rooms around obstacles, but limitations of the device was the resolution, only 2 sensors, and the author suggests that in the future a vest with more sensors have to be developed, because you cannot feel anything that's behind you or on your side. And most recently, in 2011, people have probably seen this in Gizmodo and other blogs, Steve developed a glove that you can wear on your hand with 2 ultrasound sensors, again, that give you depth information. And those are the sensors, and those are servo motors. So you actually go like this with your hand, and you feel the depth in your hand. So this way, again, you can be blindfolded and kind of navigate into a room. So as you can see, everybody uses the torso. So why is that? So based on all this research and on previous research, the skin covering your torso is actually half of the skin of your whole body. It's actually very sensitive. But if you compare that with a finger, we have a spatial resolution of 1 millimeter on the finger, 20 to 40 millimeters on our body. So the conclusion is we can use a torso, but we have to be, the grid we're going to use, it has to be coarser. So our contribution to the scientific community is that we want to explore tactile feedback on various parts of the body, not only the torso, but we want to see what happens on the legs, for example. Can you feel obstacles that, like a ball or a rock, and hands as well. And the resolution of the devices, as we have already seen, is low. We want to go bigger. We want to see what happens if we put a lot of these sensors around us. And except from the preliminary study that Jones has done, nobody has actually used actuators. Everybody used tactors, vibration motors. So we want to look at that as well.
Okay. So obviously there's some technical differences between ours and what's previously done, but there's also one big, more philosophical difference, and that's everything we've seen so far has either been some sort of active device that you scan. If you take someone who's blind, they have to use a cane. It's an active process. The scanning device in the glove is active, or it's been some sort of detection idea where it's been more of a warning system. What we want to do is we want to hopefully take this, and by scaling it up to the whole body, we're going to take it and make it more of a passive system. So for someone who has good vision, you don't have to really think about navigating through a room. You can walk around this table because you see the table, you know where it's at. It's not much of a problem. So we want to make this a natural process for people. Something where they just fill this table and know, okay, without even thinking that they have to step a little bit over to this side. as opposed to that side. The only difference is you won't be seeing the room, you'll be feeling the room. So that's kind of what we hope to get with this, or something where you're actually feeling all the objects around you in hopefully a very natural way. So our design goals are to design and construct this tactile display throughout the body using the chest, arms, hands, feet throughout. The more trigger points we can get, it's basically equals a higher resolution. The more the better. Also some challenges that as we wear this, it's going to have to be lightweight. You can't like strap a car battery on someone's back and have them go skip around campus. And it's got to hold up, at least to some degree, from everyday moving around. So just to give you a little bit of idea, we're going to be placing sensors to start with. We're going to start with maybe some on the arms, the feet, or just the chest. And as we get going, scale up. One advantage this has over people with normal vision is we can actually put these all around you, across your entire body, so you can get a 360 view of the room. It's not just which way you're facing, you'd be able to fill the entire environment. We're going to use sonar to hopefully detect distance, and then one thing we were hoping to add on, we have to look into the possibility of this, is using some sort of infrared sensor to be able to detect if it's the body heat. So you'd be able to tell not just that there was an object here, but that was a person. So you'd be able to do that and maybe look at different types of tactile feedback for the different things. So as you can see here with these just fantastic drawings that I did up, the closer you are to the wall, you'll get a greater feedback, whether it's pressure or vibration. This side's closer to the wall, so it's greater pressure. This side's away. This arm, there's a desk, so he gets a greater sense of pressure here, and this side, there's nothing, so he really doesn't get any feedback there. So, one of the big things that we're going to do different than other people, we're not against using vibrations for maybe certain areas. Perhaps it's possible for certain areas of the body or certain things. Vibrators will be the best thing, but for the most part, we want to make a grid of something with actuators where it's based more on pressure, and that's to hopefully gauge the subtle distances and make it more natural. If you use vibrators, you're either going to have things vibrating all over you all the time. That's going to be a little distracting. But if it's a subtle pressure on this arm versus none on this arm, then that'll be a more natural state. Plus, they can tell you the distance a little bit better. Like we've seen, it's kind of hard to tell the difference between how fast something's vibrating or whatever. But with pressure, you can say, well, that side's pushing harder than that side. We looked briefly into the maybe some sort of electro-tactile stimulation. Some inherent problems. One, you don't want to electrocute people. They tend to not like that. Two, one of the more real-world problems is that these things can vary quite a bit depending on the moisture in the air. If you're sweating, you'll get a bigger current through that, and that would throw off the system and throw off the calibration pretty easily. Plus, if you use it for a long time, then it does become painful. So who can use this? Obviously the first thing that everyone thinks of about something like this is, oh, someone who's blind or visually impaired. Absolutely, yeah, they'd be a great person to use this, but we feel that there's a lot of other applications for this too. One is something like a fireman. You go into a house, it's filled with smoke, your vision drops way down, you can't hardly see. Something to this degree that would help you be able to tell if you were walking past a doorway or if an obstacle was in front of you or behind you, could really help add to your senses. We're not looking to necessarily replace the vision for the normal people, just add to it and give them another way to sense their environment. Another way is we were talking earlier in the semester about bikers and the traffic around them. This would allow you, and maybe for a biker you could scale this down to something smaller just across the back, but this way they could feel the traffic around them. As you can see in this picture, there's like a truck kind of turning behind her. She'd be able to feel this and know that there's something coming up on her side real close, or whatever. Same thing if you're running, using earbuds, or possibly even something like this could be installed in like a car seat. So while you're driving, you could kind of feel the the effects of everyone around you. And then I think we've all woken up in the middle of the night, stumbled around, kicked the dog, stepped on a toy, and tried to make our way to get a glass of water or something to drink. What you could possibly do is just throw this real simply in a pair of slippers. You wake up, you slip on the slippers. You don't have to turn the lights on and wake up everyone else in the room or in the house. You can just kind of make your way through the hallways at night.
If you go back,
Yeah.
application to a bicyclist is very interesting because you have a platform to work with and you have power. So you could put a small generator with a battery, and the person could plug into the bicycle, and then have all of these sensors that they could have. I mean, it's sort of a specialized thing,
Right.
in terms of safety, in terms of understanding what's going on, you could put sensors on the bike rather than the person.
Right, yeah, and that, I didn't think about the bike, but that was kind of what I was thinking with the car, where it might be not so much a vest, but the same idea. But yeah, with the bike that would work too. And one of the reasons why we're talking about this is, you know, we looked at different things on the glasses and stuff, and the problem is, I mean, if you look at this right here, this is what we're coming to with all our sensors, and you can't really make out one thing that's going on. It's too much. It's information overload. So you start throwing up all these gauges and displays in front of you, and all of a sudden you got all these things about what's going behind you, but you can't see the road in front of you now. So this will hopefully allow like bikers to be able to focus on the road in front of you, focus on what's going on in front of them, and much like the audio dilation, instead of that all being jammed up into one thing, what we're doing is we're splitting that up to another sense. We're allowing your sense of touch to take over some of the responsibilities of figuring out what's going on around you.
Okay, so I'm just going to expand on the working principle and some of the hardware that we're using. This is the general concept that we have. It's based mainly on ultrasonics and using rangefinders that are readily available. So basically, we have our test subject, and has a collection of these transmitters and receivers on him that he's setting off ultrasonics, and he's getting information back from what's around him. And depending on how we set up the thresholds for how close something is, or whatever, we can set an alarm to go off, or some vibrator, or some force sensor or force actuator on the subject. But also, what we want to do is focus too on the human aspect too. Just if there's humans in the room, or if there's other people coming up from behind you, or they basically emit infrared, or they're detectable by infrared. So we can have an additional, where we can separate this out is have the ultrasonics based on force feedback on the skin, and then have the infrared, maybe as a vibration or some sort of tingling when there's another person near you. Yeah. And then, so this is some of the hardware that we've identified to use for this project. And this is specifically for the controllers and some of the tactile feedback. Obviously, the Arduino setups would be nice for our controllers. And then we have these standard cell phone type vibration pancake motors, and then some of these other actuators. That's a vibrator. Then this is also basically just like a speaker, which is another type of vibrator. The advantage of something like this over something like this is this has a really limited frequency range. So if we wanted to do sort of like a frequency feedback, this only has a range of from 20 hertz up to 200, whereas this basically has a really wide range, from tens of hertz to kilohertz range. And then we have so that's using vibrators for one type of feedback, and then using actuators for another. This is where it's actually pushing down on the skin. It can either be like a linear actuator, where it's just it's extending some sort of rod down on the skin, or it can be like a servo motor where you're rotating like a lever and that's pushing down on the skin. And then turning attention to the sensors, then there's readily available sensors, both ultrasonic. So these are three types of rangefinders, basically. So some of these have the transmitter and receiver split out. So this is an infrared, for example, so this is sending out an infrared wave, and then this is side's receiving it. And same thing with the ultrasonic. And this one's basically just an all-inclusive one where it's a transmitter and receiver both in the one device. And then finally, this is just like a motion sensor. This is something that's typically on like house or garage lights where it detects just motion. So as far as body placement goes, I know this looks like a lot. This probably would not be the entire. We wouldn't make a whole entire suit this semester, but we want to focus mainly on this area, and time permitting, we did kind of expand outwards to moving towards the head or the feet, and maybe some like the extremities too. But mainly focus like in this area, like on the chest, because that's easy and it's more stable. If you're trying to detect motion and your arms are walking, or when your legs are moving and your arms are moving, it makes it a little bit more difficult and probably introduces some noise into the situation. So focusing more mainly on the chest area is probably what we want to do for emitters and detectors. And when I say actuator mesh, what we're thinking about is basically making this like a grid of either vibrators or some sort of force sensors for force feedback. And then just some like functional considerations. One possible problem we might have is just the interference between two transmitters. So if we have kind of like a really dense coverage of the space around, do we want like overlapping, or do we want this to be more spaced out? Can we get away with gaps in what we're receiving? That's something that we're going to test pretty shortly. And also, I mentioned this before, but since we have two sources of information, which is basically the human infrared and also the ultrasonic obstacle detection, basically requires at least two different kinds of tactile feedback, which we have with either vibrators or using force measurement or force pressure. And then also we want to kind of like build in possibly this might work as like a cell phone app or something that you can kind of like select the sensitivity depending on what your situation is, because if you're just like sitting down in a sofa or something like that, you don't want to have the room constantly buzzing around you, so you might want to turn it off, or you might want to change the sensitivity depending on what situation you're in. And then we move to testing. So we have our weight belt level test. Basically, this is just going to be blindfolding somebody in a room and walking through an obstacle. And then for our second test, basically we're going to navigate someone through campus and throw them into traffic or something like that. No, we won't do that. But when we say real world, basically we'll make sure they wear a helmet and knee pads and all that, and we'll have two people on either side of them to make sure they're okay.
These will be supervised, but not stuff.
Everybody navigate someone. Are you going to be the?
We're gonna.
And
Unlike the colonoscopy, we're willing to take this chance, go through this.
Yeah, and for this last test, which we're kind of dubbing our ninja test, basically gonna blindfold somebody and throw probably just like beach balls at them. In fact, I think Victor's volunteered for being our test subject for this one, and see if they can avoid the objects. Okay, so this is what our timeline is. We kind of split this out into kind of like the initial like testing and prototyping phase, and then a building phase, and then a testing phase. So basically, the rest of this month, there's not much left to it, but we're just going to be obtaining the devices that we need and start doing some initial testing, and then most of March is dedicated to building and evaluating, and then finally in April we'll wrap up the construction and do some testing. So the roles for this, Brad, our communication guy, he's going to work on constructing the wearable interface. Like where should we be putting some of the stuff? What makes the most sense? Evaluating the prototype. I'm going to be evaluating most of the hardware and designing some of the circuits that are needed for this. Victor's also going to be evaluating some of the hardware, and he's going to design some of the software that's required and some of the control software as well. And of course, we're all going to contribute to the overall design and the testing.
Questions?
Can you talk about some more details about what the subject's going to wear? I mean, the actuator's got to be like woven into some kind of like spandex vest or something. It's got to be close to the skin or be effective, right?
Yeah, well, it's going to depend on which one of the actuators we go with. Different ones are going to need different things. Like if we go with the linear actuator, then we'll probably need something for it to push against. Stupid Newton's laws and whatnot. And so we were already discussing maybe making just like a little box that can push up against. To start with, we're going to use, however we do this, we're going to put them on Velcro straps for now. We're not going to build like a full suit. So we're going to start with maybe just a central Velcro strap and then scale that up from there. But yeah, we've thought about that. And the thing is it depends on what sensors we go with. One of the vibrating motors will need less of a machine to them than all we would need is some sort of spandex and maybe a little bit of a buffer.
Like the sensors, like an infrared sensor, you've got to wear that outside of your outer garments, right?
Yeah.
So, we can see, so it's kind of more than one layer of thing you can wear. You can multiple things, and it's going to be either inside or outside of the clothing.
Yeah, everything right now is hopefully we're gonna design it with any of the vibrations or the servos to work and be able to be felt outside of the clothes, so that way the whole unit can sit on top of what you're wearing already.
By wearing a t-shirt though, not wearing a jacket.
Well, there's a consideration of there's opportunity cost to implement this artificial tactile sense, if that would sort of confuse or interrupt a lot of tactile information that happens in the world already anyway, such as the cyclist example, where while biking you hear and feel a lot of vibrations that cars just naturally give off. I wonder if there is a way to maybe fall into the stream of tactile information that is already produced rather than creating representations of tactile information.
I think that's where, for bikers and for uses, this would be different things. And like for a biker, it would be a much, at least how we envision it, a much smaller thing to hopefully not overload you. Yeah, if you got a whole vest going with vibrating here and pushing up, I would probably struggle even just to stay upright on the bike. But maybe if it was a smaller strip, then hopefully that won't interfere as much.
I think this is a fascinating concept. It's very innovative, and where you could even go in the future if you were looking for funding to do a larger study later would even be the Department of Defense, because they would be interested in this for military forces. It's a very, very interesting concept.
So on that thread, actually, there was a project. I don't know what happened to it. It was called the Tricorder Project, and basically the idea was to detect incoming lasers from snipers, and it was a Department of Defense project, so that if a sniper were trying to shoot you or one of the troops, some sensor would go off, and you can imagine your infrared sensor, because most of these might be infrared lasers because you don't necessarily want to paint the dot on the target, or maybe you do. You can imagine your suit being able to detect that, so they're definitely sort of DOT applications. And I was wondering also, separate from that, because I really, the bike kind of idea, it really resonates with me, the fact that you are so focused on the task, trying to ride your bike and not get killed with all the feedback, input you're getting from the front. You are very blind around you. And I was wondering, in terms of extrapolating to driving a car and so forth, the cars obviously have some of this technology already. When you move side mirrors, there's a little blinky thing that shows you the car is oncoming. And so, in that regard, I was thinking, what if you were to decouple the sensing mechanism from the vibration mechanism? so that you can wear the vibrator on your arm, but you can put the sensor wherever you choose. So let's say you're driving a car, maybe you would just stick it outside your car, so you have a sort of sense of the traffic around you. Or if you're, like Bob was saying, riding your bike, you may want to, attach the thing behind your bike or something like that. Right? So is there a way to design it so that maybe those two things are decoupled? And then maybe you can then say, okay, what if I put these sensors in a room, in different parts of the house, and I wore this, then I have a sense of what's going on in an environment. Right? This sort of brings it into the cloud idea, right? With the third tenet of human identity was, cloud intelligence could potentially make you smarter about your ways. So when an intruder comes in, something tingles, and you already know there's an intruder somewhere, right?
Yeah, I mean, there's no reason that the sensors and the vibrators have to be together. Again, I think that would depend on your application in the car or the bike. Then you'd want them separate. Maybe for a blind person, one of the things we were thinking about is maybe too putting the sensors all over, but just building the grid of your environment just on the chest area. But that comes down to what's going to be more intuitive to a user. Will it be filling something on the arm, or will it be learning this grid system on the chest? And we're not sure yet. That's one of the things we have to test into. But so yeah, we were already talking about moving the sensors away from the vibrators. And does that work? Does it not work? And I think that would come down to whether you're trying to walk around or if you're doing something specific like driving a car or.
And then the last comment before we have to switch to the final group for today is, I know there's several groups left, but I think we only have time for one more. And maybe what we'll do is the next group will be the asthma, since you're here. Was that one thing you might consider, if it works out in your grand scheme of things, is that you may, in some cases, I know you wanted the array of sensors for the vibrators for the vest. We could potentially buy you one of these, and you could try one of these out. It's $150. It's a vest that has Tactile on them. It's designed for these video games where you feel you get shot. They actually